I'm very happy to say we have Henry Koren here to talk about image quality metrics and reducing cross-lab variation. And Henry Koren is Director of Engineering at Imatest, and he is chair of the IEEE P1858 Camera Phone Image Quality Working Group. Excuse me. Henry received his BS in Computer Science and Engineering from the University of California, San Diego, and we're really happy to have you here to give us this information and update.
Good afternoon. I'm going to be talking about the sources and means of reducing the variation of objective image quality metrics obtained from different imaging test labs. This talk is focused on some of the metrics which are part of the IEEE Camera Phone Image Quality, or CPIQ standard. Our goal is to certify multiple test labs to score mobile devices. I'll give a little history about the progress of work with the standard. We started work 13 years ago. We've had a great number of contributors across the imaging industry. We published the first version of CPIQ 1858-2016 at the beginning of 2017, then began the process of establishing and validating the procedures for executing these standardized tests. I include the ISO standards in this timeline because their work is strongly linked to what CPIQ is trying to accomplish. We want to build upon the work of other standards rather than duplicate their efforts. Our standard is subjective viewing conditions, or is an objective perceptual-based image quality metrics. These are scored in just noticeable differences, or JNDs. There are 7 metrics in the 1858-2016 standard. And these are the quality loss that we have for each of these metrics is in the subjective viewing condition of a high-resolution computer monitor where the image is filling the screen. These are the drivers of variation for some of these metrics. We're going to talk about the metrics that had significant variation in quality. A couple of the metrics, lateral geometric distortion, lateral chromatic aberration, these were high quality or low variation metrics. So there's not a whole lot to talk about here. Those align very well. Where does variation come from? Mobile devices are black box cameras with dynamic image signal processors. They have nonlinear spatial processing. They have automatic exposure, automatic white balance, autofocus. In capturing the images, we try to use the camera in an ordinary way, avoiding special modes where most users are not going to access those modes. So labs had many varying factors which the black box camera reacts to. The mobile device is scene dependent, and the test labs have a hard time in replicating the exact same scenes. Humans are the other major driver of variation. They construct the labs in different ways. They don't necessarily follow the procedures correctly. They're involved in sorting the images and implementing the analysis algorithms. The only way to truly eliminate variation is to eliminate all the humans. Just kidding, sort of. In order to validate our standard, we performed a series of round-robin tests. We shipped a collection of devices between a set of labs where each one was tested. The first round-robin study was based on the loose requirements of the initial standard. The amount of variation we found was unacceptably high. We improved our test procedure and performed a second round-robin study, which brought the variation down significantly. But some devices still perform in an inconsistent manner between exposures and between labs. And you can see that the number of devices or the number of images per device increased significantly, and I'll explain why here shortly. So we tried to control the illumination within the lab environment. We created a set of light levels meant to approximate common conditions experienced in the real world: outdoor, indoor, and low light. Some of these conditions were not easy to implement. Most labs were not able to follow the recommendation for an outdoor light source, which includes infrared. We'll be exploring what that leads to. we found that controlled illumination didn't do enough to reduce variation. For sharpness, SFR sharpness tests, in the first study, some devices randomly failed to achieve focus on our resolution target. This especially happened in low light. To address this, we decided to capture 10 exposures, refocusing between each exposure to ensure that we got at least one sharp image. Then we selected the best image from that collection. Autofocus repeatability standard will be added in the future to address the failure of autofocus. Other corrective action we took was to ensure adequate chart quality by using a large size chart where the quality isn't going to cause a loss of MPF. And so yeah, here you can see where we had an autofocus miss, and that led to 27 JNDs of quality loss. So it would have completely destroyed that phone's score if we had kept that in the ranking. These are the results of the SFR variation for the sharpness test within the 3 different lighting conditions. Devices performed the best in daylight, which is not a surprise given the small size of their pixels. As results were worse in low light conditions, we suspect that scene luminance and the resulting noise could be related to the loss of quality. Target contrast variations could be a factor as well. We're still investigating the full root cause of this variation. Exposure is scene dependent. We controlled for scene illumination, but labs were not overly concerned with target reflectance, which is the other factor which drives scene luminance. Here you see that we had specular reflections on the target, which caused the ISO speed to drop down significantly. Here we had a lab that had a darker background, which caused the exposure to select a higher ISO speed. Reflectance determines luminance, which determines ISO speed, which impacts visual noise and texture blur. To improve alignment between these results, we need to conform with the framing and reflectance requirements of the ISO standard, which calls for 15 to 25% reflectance. Although we should ponder whether this is truly representative of actual real-world scenes. Here is the variation of visual noise. We actually had more variation in the outdoor condition. Many results were able to agree closely, but some continued to vary wildly in low light. To improve this further, we suggest the standardization on the 20 patch OECF target instead of the 12 or 16 patch versions. Let's talk about texture. Reflectance and differences of charts were not controlled here either. Our test plan called for black and white charts, but some labs used the color version. Our test plan said you should use black and white charts instead of you shall use black and white charts. Don't ever use the word should in writing your standards. So these different charts had different spatial frequency distribution and disparities in both luma and chroma. Variation was compounded by reflectance and exposure differences. So we really need to control for chart frequency distribution. Texture blur was found to be the largest driver of quality loss in mobile devices, and the most variable. Here you can see that texture quality loss got worse as the illumination of the scene dropped. These disparities need to be addressed before texture results can be reliably compared between labs. Let's talk color uniformity. All of these images are from the same device. Some of this is from the phone, and others are because of the color uniformity and spectral contents of the light source. We need to establish a means of validating acceptable target color uniformity. And so here you see, in one lab, we got almost 10 JNDs of quality loss. And in other labs, we got just one JND. So this is not just the device's fault. This is related to the light source. So to explore this, we used a couple different light sources that we knew had very good uniformity. We wanted to consider illuminant, which is the most difficult to reproduce within a test lab. So we selected the daylight, or illuminant D. So our standard calls for 5,000 Kelvin color temperature daylight source. And so we used a couple different sources for producing daylight. The first was a phosphor-based LED with a 5100 Kelvin color temperature. And you can see by the spectrum of this drops off mostly around 730 nanometers. Does not have any significant infrared content. And then we used an integrating sphere with a tunable LED, which has actually 32 different channels of LED, which combines together. And this can simulate daylight up to 1,000 nanometers. This is the Gammon Scientific RS7. And then here you can see what the spectrum of actual D50 daylight looks like from our sun, which is a difficult thing to reproduce in the lab, or costly. Our typical imaging LED labs, LED and fluorescent sources lack infrared. So this is the effects on these 11 devices with this source without infrared in blue and with the near infrared in red. So the differences between infrared and no infrared averages about 3 JNBs, but did get as high as 0.6 JNBs. Did I say 3? I meant 0.3 JNBs. One device had almost perfect color uniformity with and without infrared. Superior filtering and processing can totally eliminate color uniformity. That device proved it. We have plenty of environments that use daylight lights without infrared. So calibrating and testing in both of these conditions is part of a complete characterization of an imaging system. Chroma level is a metric which can also be impacted by infrared contents. Humans like a little boost in chroma beyond accurate chroma of reality. These exposures align closely with each other, except for one with a more reflective background, and one where spot metering was enabled. Spot metering happens when you touch the screen, which leads the ISP to boost the chroma, which improves the perceived quality of the touched area. To address this, framing requirements should be strictly followed. You should minimize non-chart and non-background regions around the color target. And take care not to touch the screen to enable spot metering before taking the picture. So we have assembled these and many more procedures into this test plan document, which along with the CPIQ standard is available for purchase at this link, bit.ly/lab variation. To summarize this work, black box cameras vary dramatically based on the environment and the operator interactions. Current standards alone are not strict enough to get alignment between heterogeneous test labs. And detailed procedures can help make results independently reproducible, but some cameras just behave unpredictably. There is lots of future work. I would like to publish this complete image set and further analyze all the collected images and determine the absolute root cause of the variation. I want to further tighten the testing procedures that we've established and align better with the ISO 12233 reflectance and ISO 19567 texture technical specification chart definition. I want to help these labs to correct their improper lab setups. I want to use reference devices from these round-robin studies to audit these labs. Eventually, I want to apply the Grubbs test to identify outliers and establish an acceptable level which would lead us to certify a test lab. And only at that point am I really comfortable publishing test results from this work? So, you know, it's relatively easy to take one proprietary lab and test one device within it, but we really want to create a scoring system that is better than that. And so thanks very much to my co-authors, Vikram Sunjaro, Benjamin Tsang, and thanks to Elaine Jin, Margaret Belska, Jonathan Phillips, and all the contributors to ISO and CPIQ. I'm happy to answer any questions you have.
Very much. Thanks, Henry. It was great to get that new information. Who has a question for Henry? Any clarification?
Hi, great talk. Thank you. So some of the attributes you mentioned, the cross-lab variations is less than 1 JND. Right, so those are acceptable to be saying it's okay, the current process.
I guess it could be, and you know, I think it matters how it's reported, and you know, if that could, say we have that 0.6 JND, you know, that could push, you know, that could push a 0.4 JND up to a 1 JND. So I guess it depends on rounding. I mean, I'd like to have those as low as possible, but I guess that is one of the existential questions on, you know, what is the minimum amount of variation we can actually accept. I don't have an answer to that right now.
Okay, so I think my question is, you wanted to benchmark on individual attributes or on total? If it's on total JND, then you use Minkowski pooling based on multivariate formalism. That means your small difference will be wiped out.
Yeah, I mean, if you combine them all, yeah, that is also one of the ultimate goals, and maybe all the concern we put around infrared is overblown, and yeah, I think that the texture problem is much more serious, and that needs to be the top priority to address.
Are there other questions? I have some questions. The first one is more just a simple pragmatic question. You talked about for autofocus that you select the best of 10. That's like a new process, or I can't remember if that's part of the process. What is the method that is the refocusing method?
So we put a card in front of the camera and focus on that and then pull it away.
Okay, so an occlusion to the
yeah,
optical path.
Yeah, and I think it's better to be a card with spatial contents on it, because if it's a diffuse card, the phase detection autofocus gets very confused. The laser focus goes to close distances, is not confused, but it doesn't really treat those two systems equally. So,
got it.
And the ISO standard, Kevin Matherson is leading, is very good on that, and I think it's also a work in progress. And I think they're going to use a texture chart instead of the SFR for that, as far as I know.
Okay, and my second question relates to the texture measurement. And you talked about different elements that created that variability. I'm not sure if you mentioned capture distance or framing. Was that part of it as well, or it was specified enough people were capturing at a...
I think, I mean, you saw the variation in SFR go up at low light. So if you're losing SFR, that's gonna affect texture as well. So those are not completely orthogonal.
I see. Got it. Okay, yep, good to hear about that. And then the new document that you're talking about, the test plan supplement, that is currently available?
Yes, it is.
Yes. Okay.
With all its imperfections.
Standards and imperfections? Oh. Let's thank Henry for giving us the update on the IEEE work. Thank you very much.
Thank you.